An electric dipole comprises of a positive charge and a negative charge separated by a finite distance. Consider a dipole with a positive charge plus Q placed at A and a negative charge minus Q placed at B at a distance of 2A. This distance between the charges is referred as the length of the dipole. For an electric dipole, the midpoint O of the line joining the dipole is called the center of the dipole, and the straight line passing through the charges and also through the center is called the axis of the dipole. Assume that the dipole is placed such that the center O of the dipole coincides with the origin and the axis of the dipole coincides with the x-axis of the Cartesian coordinate system. The charge minus Q is placed along the positive x-axis, and the charge plus Q is placed along the negative x-axis. The product of the length of the dipole and the magnitude of the charge is called as the electric dipole moment, P. Here, P is equal to 2AQ. It is a vector quantity directed from minus Q to plus Q. Let us now obtain the electric field strength, E, at a point P on the axis of the electric dipole, which is at a distance x from the midpoint O of the dipole. The magnitude of electric field strength E due to a charge Q at a distance r from it is given by E is equal to 1 by 4 pi epsilon naught into Q by r square. Following the expression, the magnitude of the electric field strength E1 due to the charge plus Q is equal to 1 by 4 pi epsilon naught Q by x plus a square. Let this be equation 1. The direction of this electric field is in the direction opposite to that of the dipole moment. Similarly, the magnitude of the electric field strength E2 due to the charge minus Q is equal to 1 by 4 pi epsilon naught Q by x minus a square. Let this be equation 2. The direction of this electric field is in the direction of the dipole moment. The point P is nearer to the charge minus Q than the charge plus Q. As the distance of the point P from minus Q is lesser than that from plus Q, the magnitude of the electric field strength E2 is greater than E1. Hence, the magnitude of the resultant electric field strength E at the point P is equal to E2 minus E1. Let this be equation 3. The direction of the resultant field strength at the point is in the direction of E2. Substituting the values of E2 and E1 and simplifying, we get the expression for the electric field strength E is equal to 1 by 4 pi epsilon naught or AQX by x square minus a square whole square. Let this be equation 4. Simplifying equation 4, we get E is equal to 1 by 4 pi epsilon naught 2x into 2AQ by x square minus a square whole square. In this equation, 2AQ is the magnitude of the dipole moment P. Therefore, E is equal to 1 by 4 pi epsilon naught 2px by x square minus a square whole square. Let this be equation 5. When the point P is at a very large distance from the center O, then x is very large compared to A. Then, writing the expression 5 as in equation 6 and neglecting the term a square by x square for x which is very large as compared to A in equation 6 and on further simplification, we get E is equal to 1 by 4 pi epsilon naught 2px by x power 4. Let this be equation 7. This can be further simplified as E is equal to 1 by 4 pi epsilon naught 2p by x cube. Let this be equation 8. In vector notation, equation 8 can be expressed as E is equal to 1 by 4 pi epsilon naught 2p by x cube into p cap, where p cap is the unit vector along the dipole axis in the direction of minus q2 plus q. Let this be equation 9. Let us now obtain an expression for the electric field strength at a point S on the equatorial plane of the electric dipole. Let point S be at a distance y from the center O of the dipole. The point S is at a distance r and is equal to root y square plus a square from each charge of the electric dipole. Let this be equation 10. At the point S, the positive charge creates an electric field of magnitude E1 is equal to 1 by 4 pi epsilon naught q by r square. Let this be equation 11. Electric field strength E1 is directed away from the positive charge and acts along the line joining the charge plus q and the point S as shown. Similarly, the negative charge creates an electric field of magnitude E2 is equal to 1 by 4 pi epsilon naught q by r square. Let this be equation 12. Electric field strength E2 is directed towards the negative charge and acts along the line joining the point S and the charge minus q as shown. We observe that the magnitude of E1 is equal to that of E2. The point S lies on the perpendicular bisector of the line joining the charges plus q and minus q. Hence, by geometry of the triangle SAB, the angle SAO is equal to the angle SBO. Let this angle be theta. Now the angle E1SE2 is the exterior angle of the triangle SAB, and hence this angle is equal to 2 theta. The resultant of E1 and E2 is obtained by using the parallelogram rule for vector addition. According to the rule, the resultant of E1 and E2 is obtained by the diagonal of the parallelogram formed by the vectors E1 and E2 as the sides. Since the magnitudes of E1 and E2 are equal, lengths of the vectors representing E1 and E2 are also equal. Hence, the diagonal of the parallelogram formed by the vectors E1 and E2 as sides bisects the angle 2 theta. Thus, the resultant of E1 and E2 makes an angle theta with the direction of both E1 and E2. By geometry of the figure, the resultant of E1 and E2 is parallel to the x-axis and is directed along AB. Let us consider the components of E1 and E2 along the x and y axes to find the magnitude of the resultant electric field at the point S. The components of the electric field E1 along the x and y axes are E1x and E1y respectively as shown. And the components of the electric field E2 along the x and y axes are E2x and E2y respectively as shown. Since the electric field strengths E1 and E2 are equal in magnitude, the components E1x and E2x will be equal. Similarly, E1y and E2y are also equal. We also observe that the components E1y and E2y are oppositely directed and hence they cancel each other. Therefore, at the point S, the resultant electric field strength E is equal to E1x plus E2x. Let this be equation 13. As the angle between E1 and x-axis is theta, the component E1x is equal to E1 cos theta. Substituting the magnitude of E1, we get E1x is equal to 1 by 4 pi epsilon naught into q cos theta by r square. Let this be equation 14. Similarly, the angle between E2 and x-axis is theta, and hence E2x is equal to E2 cos theta, which is equal to 1 by 4 pi epsilon naught into q cos theta by r square. Let this be equation 15. Substituting equations 14 and 15 in equation 13 and simplifying, we get the magnitude of the electric field at the point S. E is equal to 1 by 4 pi epsilon naught into 2q cos theta by y square plus a square. Let this be equation 16. From trigonometry of either of the triangles SAO or SBO, we get cos theta is equal to a by r. Substituting the value of r, we get cos theta equal to a by square root of y square plus a square. Let this be equation 17. Substituting equation 17 in equation 16 and simplifying, we get the equation for the magnitude of the resultant electric field strength E at point S. Since the dipole moment P is equal to 2aq, we get E is equal to 1 by 4 pi epsilon naught into P by y square plus a square whole power 3 by 2. Let this be equation 18. The direction of the electric field strength at the point S is opposite to that of the electric dipole moment and parallel to the axis of the dipole as discussed earlier. When the point S is at very large distance from the center O, then y is very large as compared to A. Then, writing the expression 18 as in equation 19 and neglecting the term a square by y square for y which is very large as compared to A in equation 19, and on further simplification, we get E is equal to 1 by 4 pi epsilon naught P by y cube. Let this be equation 20. In vector notation, electric field strength E can be expressed as shown in equation 21. The minus sign is used since the electric field strength E is opposite to the direction of the unit vector P cap. For a given dipole, the magnitude of the dipole moment P is constant. From the expression of the dipole moment, we get charge Q is equal to P by 2A. Hence, as the length of dipole 2A tends to 0, the magnitude of the charge Q tends to infinity, so that the dipole moment P is equal to 2AQ becomes finite. Let us now look at the physical significance of a dipole. A molecule having positive and negative ions possessing charges of equal and opposite magnitudes behaves like an electric dipole. In certain molecules, known as non-polar molecules, the centers of all positive and negative charges coincide. Hence, in such molecules, there is no dipole moment set up. However, when a non-polar molecule is placed in an external uniform electric field, the electron orbits get distorted due to the force exerted by the external electric field. This results in the separation of the centers of positive and negative charges. The negative charges move in the opposite direction of the electric field, whereas the positive charges move in the direction of the electric field. This motion of the charges now sets up an induced dipole moment for the molecules, and the molecules are said to be polarized. When the external electric field is removed, the polarization disappears. Hence, the induced dipole moment also vanishes. Carbon dioxide, CO2, and methane, CH4, are examples of such non-polar molecules. There are other types of molecules called polar molecules, where the centers of the positive and the negative charges do not coincide. They possess some dipole moment even when they are not in the presence of an external electric field. Such molecules are called polar molecules. These these are permanent dipoles. When such polar molecules are placed in an external uniform electric field, they orient themselves in the direction of the field. Water molecule H2O is one such polar molecule. Consider a permanent electric dipole having a positive charge plus Q at A and a negative charge minus Q at B, separated by a distance 2A. A permanent dipole is one which has a dipole moment irrespective of the presence of an external electric field. The electric dipole moment P of the dipole is equal to 2AQ, directed from minus Q to plus Q along the axis of the dipole. Let the electric dipole be placed in a uniform external electric field of strength A, with its axis AB making an angle theta with the direction of the external electric field. Now, the charge plus Q of the dipole experiences a force F is equal to QE in the direction of the external electric field, and the charge minus Q of the dipole experiences a force F is equal to QE in the opposite direction of the external electric field. We see that on the dipole there are two equal and opposite forces along different lines of action, and hence we can say that the dipole experiences a couple which is the net torque on the dipole. This couple rotates the dipole until it is aligned with the direction of the external electric field. However, the net force on the dipole is zero, since it experiences equal and opposite forces. Since the net force on the dipole is zero, the couple on it is independent of the origin. The magnitude of the torque on the dipole is equal to the product of the magnitude of each force F and the length of the couple arm AD. The torque tau is equal to F into AD. Hence, tau is equal to QE into AD. In the triangle ADB, sin theta is equal to AD by AB. Since AB is equal to 2A, we have sin theta is equal to AD by 2A. Therefore, AD is equal to 2A sin theta. Substituting the value of AD in the expression for torque, tau, we get tau is equal to QE into 2A sin theta, or tau is equal to 2A QE sin theta. But the dipole moment P is equal to 2AQ. Therefore, we have torque tau is equal to PE sin theta. This is the expression for a torque experienced by a dipole when placed in a uniform external electric field. Since PE sin theta is equal to P cross E, we have torque tau is equal to P cross E. If the angle theta is equal to 90 degrees, sin theta becomes 1, and hence the torque on the dipole reaches its maximum. Tau max is equal to PE. Hence, we see clearly that the torque on the dipole is maximum when the dipole is held perpendicular to the direction of the external electric field. When the dipole is placed such that its axis AB is parallel to the external electric field, then the angle theta is equal to 0 and sin theta is 0, and hence the torque on the dipole is equal to 0. When the dipole is placed such that its axis AB is antiparallel to the external electric field, then the angle theta is equal to 180 degrees and sin theta is 0, and hence in this position also the torque on the dipole is equal to 0. From this discussion, we see that the expression tau is equal to PE sin theta will be valid only when the dipole is in a uniform external electric field. But when it is placed in a non-uniform external electric field, then the charges plus Q and minus Q of the dipole do not experience equal and opposite forces. Each experiences a force of unequal magnitude, say F1 on plus Q and F2 on minus Q, in different directions depending on the direction of the electric field strength at their respective locations. Hence, there is a net force on the dipole. In an external electric field of increasing magnitude, if the dipole is placed such that the dipole moment is in direction of the increasing field, then the net force on the dipole will be in the direction of the increasing field. Conversely, if the dipole is placed such that the dipole moment is in a direction opposite to that of the increasing field, then the net force on the dipole will be in the direction of the decreasing field. In general, the net force on the electric dipole depends on the angle made by the dipole moment with the external electric field. We know that when a dry plastic comb is run through dry hair, it gets charged by the method of friction. This dry comb can then attract pieces of paper. Here the pieces of paper are not themselves charged, but the electric field created by the charged comb induces a net dipole moment in the pieces of paper in the direction of the electric field. The electric field of the comb is non-uniform, and it exerts a net force on the pieces of paper having a net induced dipole moment. Thus, the pieces of paper move towards the comb because of the net force on them.